Okay, so let's continue on with chapter 2, talking about the different type of bonds in biological molecules. Specifically, we're going to look at ionic bonds, covalent bond, and hydrogen bonds. So let's start off by talking about how atoms can actually interact together when they're electrons. They're electrons that are on their valence shell. So if you recall, the valence shell is the most outer shell. When the electrons on the atom interact with each other, they can form what we know as molecules. So molecules when two or more atoms are able to actually interact with each other. When we have multiple molecules interacting with each other and molecules that are made of different elements, right? So you have, like, for example, hydrogen and oxygen, they can form together and form compounds. So compounds are molecules that are made of two or more elements. So the first type of bonding we're going to look at is ionic bond. So ionic bond is interesting because it's between two different attractive charges. So the example that we kind of talked about earlier was salt, right? So in salt, you have this mutual attraction between two oppositely charged ions because of the transfer of electrons. So what do we mean by that? So let's kind of look at this in a little more detail. So here we have a sodium atom. And as we mentioned before, an atom is the happiest when it's the most stable. And so in order for an atom to be stable, it needs to have a full valence electron shell. Well, that means that there needs to be 8 electrons here for the sodium to be valence shell. Either that or it needs to lose this electron so that it can have this middle layer right here, it being its full valence shell, right? So sodium right here is not very happy. Sodium wants to get rid of an electron in order for it to be stable. Chlorine atom is kind of the opposite. It actually wants to gain an electron in order for it to be happy. So it's not happy because it only has 1, 2, 3, 4, 5, 6, 7, and it wants to have 8 electrons in order for it to have a full shell. And so what happens is that you actually have sodium ion or sodium atom here able to take its electron on its lone electron on this outer shell, and it's going to actually donate it to chloride. So when it does that, now sodium's happier because sodium now has a full valence shell. It has a full valence shell here, but because it lost an electron, it actually has a positive charge. Because remember that the number of protons is equivalent to the number of electrons in an atom. So that means that now we have one more positive charge here because of the proton, because we lost that electron. So that's where that positive charge comes from. Vice versa, we have chloride. Chloride originally was neutral right here, but when it gained that electron, this electron right here, electron has a negative charge, and so it has an electric charge now because it has one more proton than it has, one more electron than it does proton, right? So that's where the positive and negative charge. So now we have this mutual attraction between two oppositely charged ions, positive and negative, and so then you have sodium chloride. And so that's how we actually have salt. And so that's one of the reasons why salt can easily be dissolved in water is because they're not actually sharing the electron. It's because they transfer their electron, sodium transfer electron to chloride, and now they're gain that charge, that positive and negative charge, that they interact together to form that salt molecule. And as always, these videos will be available for you to link on and kind of watch to get a little more information. Okay, so covalent bond, while ionic bonds are a mutual attraction, covalent bonds actually will share their electrons. So here they're actually sharing their electrons, right? So if you look at all these examples here, they're actually sharing their electrons. And as you can see, we have different types of covalent bond. We can have single right here. This is only one bond. So if we were to, I'm going to mark it as A for atom. But this could be, you can imagine this being a 2 hydrogen atom or 2 oxygen atom. But these two, we're going to pretend those are both A's. Right here are forming a single covalent bond. So I'll just draw 1 right here, right? Whereas over here, down here, we have them sharing 2 bonds. So we could think of that as A and A having 2 bonds. Okay, so each one of these bonds have 2 electrons. So here we have 2 electrons being shared, whereas here, because we have 1 bond, 2 bonds, and each one has 2 electrons, we have 4 electrons being shared here. Okay, so we can have single bond, we have double bond, we actually have triple bond. We see this a lot with carbon atoms that will actually have triple bonds. And we can have nonpolar covalent bond, which means that between these 2 atoms, they're sharing the electron equally, compared to polar covalent bond. In polar covalent bond, they're not sharing equally. So we observe that with water. So with water, while they are sharing the electrons, they're not sharing equally. So imagine 2 kids fighting over a toy. They're both holding onto that toy. They're both holding onto that toy, but one kid has that toy almost to him. He's pulling it and it's like really close to him, where the other kid's still holding onto that toy, but maybe their hands are stretched apart, right? They're fighting and they're kind of tugging war with one another, but one of them is actually stronger and has the bond closer to itself, right? So we have one kid with, let's say this is the toy. Okay, this is really bad drawing, but imagine this is a toy and it's a lot closer to that kid than this kid over here. Even though this is one singular bond, the electrons are much closer to this kid than this kid, and that would be your polar covalent bond. So because of this polarity that is observed, and we can observe this with water, with water molecule, where the oxygen is just so much more greedy when it comes to that electron. So its electron negative is negative, whereas a hydrogen is not as greedy with its tug on that electron. So it has an electron negative that's positive. What happens is that when it interacts with when there's other molecule, is that this hydrogen, because it's positive, and this oxygen, because it's negative, they will form what's called hydrogen bond. So they're not actually bonding. They're not actually, they're not even like ionic bond where they donate, right? There's no transfer of electrons happening here, but there's this attraction, right? So this guy, because he has so much electron, like this pool of electrons near him, the electrons are circling much closer to him. This hydrogen bond is like, ooh, well maybe this guy will also share an electron with me. Like it doesn't know, so it's just hovering nearby. Like it's just hoping that maybe this guy will drop the toy. It doesn't know if it will or not, because it's also, this other guy is also sharing the toy with it, but it's just attracted to how much electron energy is around this oxygen. So they are attracted to one another, so then they end up forming what's called hydrogen bond. And hydrogen bond, what's unique about hydrogen bond is, like I said, it's an attraction, and it's a weak attraction between an atom and hydrogen, but it also, when you combine multiple hydrogen bond together, it can actually stabilize something and become almost as if it was sharing it. So an example of that would be our DNA. So you've heard that our DNA is double-stranded, right? So you have two DNA strands that are kind of near each other, and they're not actually sharing, so they're not actually like forming a solid bond, like they're not combining together and forming like this. But because of the electronegative ness of a DNA between hydrogen and other atoms, this hydrogen is partially positive, and there's another atom over here that's partially electronegative, right? Similar to water. So they will combine together where they're near each other. So just imagine they're near each other. So near each other like this, if it was just 2 molecules, you can break it apart. But if you have a whole DNA strand which is full of these interactions, they will actually be so close to each other that it's almost as if they're holding hands, but they're not. They're just kind of really close to one another. And we don't want them to hold hands in DNA. Can you think of why you might not want them to hold hands? Well, our DNA, we actually, you might remember this from high school biology, or this might be new to you, but the DNA, let me move my head. I just realized it's covering this in case you want to read it. Your DNA, you want it to be double-stranded, but you also want it to be able to open up. So in order for us to have our genes being transcribed, the DNA has to actually be able to break apart, open up together, so that we can actually access the information that's in that DNA to make the genes. And genes are important because when the genes are expressed, that's how you have different phenotypes to behave. So just think of your immune system. When you have viruses that you're trying to deal with, you want to create more immune response genes in order to help combat that virus infection. So we want to be able to open the DNA where those genes for different immune response will be available. And so we want to open our DNA, be able to access that, make whatever genes we need to. But when we get over the viruses and we don't need that section open anymore, then we want the DNA to kind of interact and close off so that we don't accidentally make too much of a gene that we don't need, right? And so we'll see this a little bit more later on when we talk about gene expression later on in the series. But for now, just keep in mind, these are weak attraction between an atom and hydrogen atom that allows it to interact as if they were sharing atom, but they're not actually sharing, electrons, but they're not actually sharing the electrons. So let's look at this next picture right here. Right, so we're gonna talk about the next section. We're gonna talk about is water, but I just want to introduce this a little bit more, and kind of show you what I mean by the sharing. So water is a really important molecule on Earth. We're made of a huge portion of our body is made of water. Most organisms, huge part is made of water. Water, does a lot of unique supporting, and we want to actually see water. The water molecule itself is a polar covalent bond. So that means that the bonding here between this oxygen and this hydrogen atom and this hydrogen atom are polar covalent. So they're covalent bonds, which means they're actually sharing the electrons with each other, but they're polar because oxygen is slightly negative while hydrogen is slightly positive. And so because oxygen is slightly negative, all of these other hydrogen bonds want to be near this oxygen bond, and vice versa. These hydrogen bonds on this oxygen molecule want to be near this oxygen atom. So because you have all these positively partial negative charge and partial positive charge interacting, they're being attracted to one another, and this is a huge part of why we have hydrogen bond and why water has these different characteristics. Okay, so let's take a little bit of a moment to kind of review what we've been talking about with regards to bonding. So which bond holds multiple water molecules together? So kind of recall that we're trying to talk about, let's say, this little guy, right? And we have another one over here, which is our water molecule. Okay, I'm not doing a very good job drawing this, but that's okay. And so you have hydrogen and hydrogen. Right, and then we'll just draw it. For simplicity, we'll draw it as, I know these are not equal length, but it's just so that I can show what I'm talking about. And we'll talk about this a little bit more. But now you have these two hydrogen water molecules together, right? And as we mentioned before, because of the electron negative, this guy is going to want to be near this guy. So they're kind of interacting that way. Whereas this one is kind of interacting with this guy that way. So they're kind of interacting. This one will probably be interacting with another water molecule. But because of these interacting and wanting to be near each other, we actually have these bonds that we call hydrogen bonds, and that's what holds water molecules together, is these hydrogen bonds. Okay, what bonds occur when two atoms are sharing their electrons? Okay, so the key word that I want you guys to recognize here is that they're sharing their electrons. Okay, covalent bond, but what type of covalent bond is it going to be? Are sharing equally is going to be a non-polar covalent bond. This question specifically says share electrons equally. So here we have a non-polar covalent bond. What if they don't share equally? So that, for example, we have H2O, right? This is also within that water molecule. It's a covalent bond. But because they're not sharing equally, we actually have polar covalent bond. Okay. Hopefully that makes sense, right? And then the last question here is what bond occurs when two oppositely charged particles are attracted to each other? So can you guys think of the example that we talked about? So the example would be salt, right? Which would be when sodium, which is positive because it gave its electron to the chlorine atom, and chlorine, which is on negative because it accepted, and now because of this positive and this negative charge right here, they're attracted to one another and they end up bonding in what we call a ionic bond. They're forming an ionic bond together, and that's when two oppositely charged, positive, negative, particles are attracted to one another. All right, let's move on to water. So let's stop here and continue on in the next section, actually looking a little bit more into water.